I'm really good at not forgetting to do that this semester. Okay. So here we are, it's Wednesday, and today we're going to do, whoop, here comes Derek. See, as soon as I think everybody here, somebody else pops in. Let's wait till he gets in there, and there we go. So go over any homework questions. So today we're going to put all this logic stuff together to do, to analyze an argument, and there's a definition to an argument, and we'll see what we can conclude. So before we go into that, anybody have any questions about anything at all? Last time we concentrated on the conditional, the if-then, and all the ways there are to twist that around. Anybody got any questions?
Could we look at 46, actually, from the homework?
Yeah, number 46, hang on. And that was page, what, 48 maybe? Do you remember? Page 48. Let me see if I can pull that up. Whoops. Is that the one with compound X is boiling?
Yes.
Oh, yeah, Kenneth and I were just talking about how really simple sentences can confuse you, right? So you're supposed to, on this one, and then there's 1, 2, 3, 4, 5, 6 statements that follow, and you have to decide which are true. So did you have a specific question on that one?
Well, not exactly. I mostly, I was wondering if you had to, basically in the original sentence, whether it was whether something is a necessary condition, if that means it's not R, if not R, then not S. Well, yeah, you're using P, but
yeah,
basically just what the initial statement is.
All right, hold on a minute here. So there's the two statements, right? So we have, if compound X is boiling, then its temperature is at least 150 degrees. Right, so I've done that. So statement A, so converting them to symbols works well. Statement A says Q then P, and that is false, right? You can't just swap them. Oh, wait a minute, Olivier's coming in here, hold on. So there's A. So statement B, if the compound is less than, so statement B says if not Q, then not P, and that's true, that's the contrapositive, right? So here's our initial statement. Statement C, compound X will boil only if its temperature is at least 150. So what did you think about that one?
I thought it was false.
Okay, why?
Well, this is what I was going to ask, because I feel like I just rationalized it in my head rather than wrote it out. But because if it's saying that it has to be at least 150 degrees for it to boil, but
wait. Oh, wait a minute. Which one says that? Statement C or the original?
The original.
The original doesn't say that. You put the word, the original says, if it's boiling, then the temperature is at least 150. You said that slightly different. I forgot what you said.
Yeah, I did.
Right, you can't change the original statement. So, but this doesn't say it's not an only if. So for example, if compound X is not boiling, then the temperature is less than 150. Well, that doesn't necessarily have to be true, right?
Right.
So other factors can come into it.
Right.
So that one is, so C is false.
Yeah.
Right, which you kind of thought so. Statement D, if compound X is not boiling, then the temperature is less. So this would be not P, then not Q. And going from the original, this is inverse converse, so this statement's false, right? And then E, now we get the word necessary and sufficient. And there was a definition for those in the book. So what did you think for E?
I thought E was true and F was false.
You're right. You're correct on those. Did you just use the definition right from the book?
Well, yeah, that's what I mean. I just looked at it and didn't like. That's what I was saying. I didn't know how to write that out necessarily as much as I just thought about what it was saying and just made a guess. You know.
Well, and that's okay, because in real life, when we try and think logically about something, we don't whip out truth tables, right? We try to think of things reasonably like you're doing, and that's the kind of thing I'm pushing here. So if we go back, there is a way to write it up. I'm going back to where the definitions are here. Make sure I get it. Okay, so necessary. So R is necessary and sufficient. Oops, sorry. So R is necessary. So if R is necessary for S, or let's say if P is necessary for Q, that means if Q, then P. So that's the definition of necessary right there. So there is a way to write that out. And then sufficient, where are we? Sufficient, if R is sufficient, if P is sufficient for Q, that says P then Q. So this is another way of saying if it's sufficient, it's sufficient for the compound to be boiling if its temperature is at least 150. So it's all confusing, right?
Yeah, I mean, basically, I just looked at it and thought that E was basically the same, was an equivalent sentence to what the original statement was, just a different way of saying it.
Let me go down here. I like that you're using the word equivalent. So yes, that's correct. That's just rewording this another way. Another word for if P then Q. Another way to say this is whenever P, Q, right? So whenever can take the place of if. So you got them. It's just a matter of confidence, right?
Yeah, I just didn't know if there was like, because I didn't really show any work on anything. You know what I mean? I just wrote true, false, because I could just look at it and figure it out. I didn't know how to like, you know what I mean? If that was like a test question, I wouldn't know what I was supposed to have written.
Well, so these two things, necessary and sufficient, this is the way you write them out. So you just use that definition. Or, you know, if it's on a test question, if you can explain it in regular sentences, that's fine also. There isn't only one way to answer a question. There's wrong ways to answer a question. And as long as you're explaining it, you know, completely and logically, you're good. So there's how those go. So you did good on those.
Okay, thanks.
Yeah. So this course really pushes your level of confidence on things, right? And it's all good. It's all good to be thinking hard like this. Questions? Anybody else? Plus, that was an even one, so I don't think the answers were in the back of the book, right? All right. So let's see what we got today. So oftentimes there's a case where getting rid of words can be helpful on that. So arguments. Not like the shouting back and forth kind. Definition is two or more statements followed by statements, and these are called premises or clues. Those are called clues, followed by one statement called a conclusion. So that's definition of an argument. Oops, this is an E. So in the beginning of the semester, when we had those questions about where the treasure was by the flagpole and the Alice and Carlos problems, your conclusion, those were arguments, and you use those premises to conclude where was the treasure or that John did the crime. So those were arguments. So we're going to look at these today, how to do these logically and how we can easily be fooled here. So one type of argument is called a syllogism. A syllogism is exactly two premises and one conclusion. And here's a really famous one. So the logic we're using goes all the way back to Aristotle and Socrates and the time of the ancient Greeks, when they were trying to put together the formal rules of logic that we're using. So, all men are mortal. Socrates is a man. So here's a statement, all men are mortal. Statement happens to be true, but that doesn't actually matter in an argument. Socrates is a man. That statement also happens to be true. And what can we conclude from that? What's an inescapable conclusion from those two statements?
Socrates
is mortal.
Yeah. So instead of all men, we can see every human is mortal. Socrates is a human. And here's your new little symbol for today, by the way. Little triangle of three dots. Anybody happen to know what that is? Anybody seen that before?
Therefore.
Yeah, Michaela, good. This is the word therefore, which means conclusion, Socrates is mortal. There. This happens to be a valid argument. And we'll get into the word valid here, which valid has nothing to do with true. It's valid because this conclusion is inescapable and must follow from the premises above it. So all men are mortal, Socrates is a man, therefore Socrates is mortal. So that's called a syllogism. So I'll show you another one of these. And that's valid, right? So all dogs are mammals. Fido is a dog. Therefore, Fido is a mammal. And that is valid. Now, if you look carefully here, what's the difference between this one and the last one that I just did with Socrates? What's the difference between those two? The only thing different from this argument and the one I just did, the only thing different is the words. The structure is exactly the same. So the words don't matter. And that's an important object here. So if I say all grus are blabs, and if I say Wex is a blab, Wex is a grus, what can we conclude? All grus are blabs, Wex is a grus, therefore
Wex is a blab.
There we go. Do we know what a grus is? No. Do we know what a blab is? No. Do we know what a Wex is? No. But this is a valid argument. It's the same as this one, just the words. It's the same as the one with Socrates. So in arguments, the words don't matter at all. Those are just made up words, but that still has to be the conclusion from those two premises. And that's the power of looking at an argument logically. We don't care what the words are. We strip away the words. We only care what the skeleton underneath looks like. A valid argument depends only on its structure, not the words that are wrapped around that structure. So we're only looking at framework here. So I'm going to write something else here and show you the structure. So instead of saying all dogs are mammals, I'm changing the word all. I'm changing it to an if-then statement. If dog, then mammal. Fido is a dog. Therefore, Fido is a mammal. All right. And this is valid. If I do it this way, if dog, then mammal. And if we say Rex is a mammal, therefore Rex is a dog. Valid or invalid?
Invalid.
Invalid. Now, could Rex be a dog?
Yes.
Rex could be a dog, but based on these two premises, is it must Rex be a dog? And the answer is no. Just showing that you're a mammal, Rex could be a walrus or something like that. So here's a case where this is true. All dogs are mammals. This is true because it's a premise. We assume a premise is true. So Rex is a mammal. That's a true statement. And this could also be true. It could be true that Rex is a dog, but this argument is invalid because these two premises do not force this conclusion, even though this statement could be true. Up here, this is true. There's no escaping the fact that Fido is a mammal. So we have a valid statement, a valid argument with all statements true. We have an invalid argument, even though all three statements could be true. So that's something very important about arguments. Valid, invalid, have no connection to true or false. The words true and false only apply to a statement. Arguments can't be true, arguments can't be false. Arguments can only be logically correct or logically incorrect. You can have a valid argument where every single statement is false and the argument is still valid. You can have an invalid argument where every single statement is true, but the argument is not valid. So the forms that we just had, all the ones I just did with Socrates and Rex and Fido and all of that look like this. If P, then Q, P. All of those arguments looked like that. The words didn't matter. Let me just pull something up here. Hang on a minute. Hold on. Oops, hang on just a second. Jumps all around here. Okay. So this has a name. I'm not going to be big on vocab. This is called modus ponens. That's the name of this kind of thing. Now, so this is valid. If P, then Q. Q, therefore P is invalid. If dog, then mammal. We have a mammal, therefore we have a dog is invalid. If it's raining, then there's clouds. We have clouds, therefore it's raining, invalid. Here's another form. Whoops. Looking at this, sorry, throat. What can we conclude here? Can we conclude anything?
Not P.
Yes, correct. So this says, whenever you have this, you will have this. So if we don't have that, we can't have this. So if it's a dog, then it's a mammal. This thing is not a mammal, therefore it cannot be a dog. So this is also a valid form. And notice the words don't matter. It's only the structure underneath. And that allows us to think critically, because we all know words can have an emotional impact on us. The person offering you an argument to try and convince you of something, you might judge whether that argument's okay or not based on whether you like that person or not. We're all humans, we're all subject to that. But if you can strip everything away and become like Mr. Spock, look only at things that are logical. So we'll look at these forms. And she has a lot of great examples in there. So when you're going to do the homework for over the next few days, take some time and actually read through her examples and her explanation. She's a really good writer. So let's try a couple more. Okay, there's a premise. It is red or it is blue. So we have to assume that's true. And I'll get to that in just a minute. What conclusion can we make?
It is blue.
Yep. Has to be. The first statement is an or statement. For an or statement to be true, only one of those has to be true. They could both be true. Only one of these has to be true. So for an or statement to be true, if this part's false, the other part must be true for the statement to be true. So we can conclude this is valid. And here's why we can't use true and false. You have no idea what I'm talking about here. You don't know if it's red or blue, but based only on the evidence. So here's how a courtroom works as well. You're only allowed to consider the evidence. You can't bring in other sorts of things. Now, if we have, it is up. It is up, or it is green. Second premise, it is up. What conclusion can we make?
Can't you not really make one because it can either be not green or green and still be true?
Correct. There is no conclusion. That was good. Can't make any conclusion at all. Here we can because of this word not. So if you know in an or statement, if you know one part of them is true, that doesn't tell you anything about the other part. So here's a case where no valid conclusion can be made. Maybe it's green, maybe it's not. Doesn't matter. That wouldn't violate those two statements. So here we have a general form for the or statement. P or Q, not P, therefore Q. That's valid, right? This is a true statement because at the premise, we assume that this statement is true. So I know at least one of those has to be true. If you're told one of them is false, then the other one must be true. And if I put not Q here, I would just get a P over here. All right. So
How do you know that that's not saying, because you're saying, is that sentence saying it is either red or blue, but not both? Or that it has to be it has to include one of those two things?
So there's two kinds of or, right? Oops, sorry, Mariana's coming. She fell out and she's coming back in here. Hang on a minute. Mariana, are you back here?
Yeah, I'm back. That's Wi-Fi problems.
I'm sorry. I hope you weren't waiting long. I keep forgetting to look over there.
No, it's okay. I wasn't waiting long.
Oh, okay. All right. So Nate, back to you. So there's two kinds of or. There is inclusive. So inclusive means one or the other or both. And the symbol for that is this. There is exclusive or. And that means only one of them is true, not both. And the symbol for that is this. And we don't see that very much. In this textbook, you always assume the inclusive or unless you are specifically told. So does that answer your question, Nate?
Yeah, yes, it does. I forgot that there was the other one, but then I couldn't remember which one it was when it's the V.
Yeah, and that's the inclusive or. There's only a couple of homework. She doesn't even talk about the exclusive or very much because in everyday life, we tend to use the inclusive more often. So this would be specifically told here. So we know that this is an or statement and it's true. So both of them could be true or only one of them could be true. That's how we can come up with this valid conclusion here.
Got it.
So the exclusive or, just an example, that's like, you're sitting in a restaurant and your meal comes with soup or salad. That's exclusive or. You only get one, not both, unless you pay extra or something like that. You go to buy a new car, you can get 0% financing or $5,000 off or something like that. You only get one of those. So always assume the inclusive or in this course unless you're told otherwise. All right. Now, let's do some symbolic work here a little bit. Right. Let's analyze an argument that's more than two premises. Let me pull one up here. Whoa, 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 whoa. Let's look at, I don't like that. All right, so this is number 7. And I'm on page, I think I'm on page 60. And they give us an argument. It's going to have 3 premises and a conclusion. Okay, so there's an argument. And the homework says, now the homework talks about using truth tables to do argument analysis. And she has lots of examples of using truth tables. I would recommend you don't use truth tables. Using truth tables to do an argument, it just gets really complex looking. Plus, that's not how we navigate through the real world. We don't use truth tables. So I'm going to kind of go through these more, as Nate said earlier, by just kind of trying to think about it rationally. So we have three premises: P, if P then Q, not Q or R, therefore R. So is this valid or not? So here's how these work. When you see this letter just sitting right here, since this is a premise, you assume premises are true. So a little side comment here. This is how science works. In science, you come up with a hypothesis. In biology or physics or chemistry or something, you expect that a certain outcome will always happen, and you try and develop this law. So you go into the laboratory and you try to do something experimental that is repeatable and comes out with the same conclusion, same result every single time. If every time you do something, you get the same result, and then you publish that, and other labs all over the world reproduce it, they keep coming up with the same conclusion, you decide you found something true. If your result doesn't work, so you go back, you check all your equipment carefully, you do all that kind of stuff, make sure you're doing that right. If your conclusion keeps being invalid, then you maybe begin to question your original premises. Maybe I'm making an assumption that shouldn't be true. And this is how human knowledge grows. So we assume all of these are true. So 1, 2, 3. She doesn't number these premises, but I'm going to. Since this P is sitting here just by itself, remember, P is a statement. It represents, I don't know, the moon is made of cheese or something like that. We assume it's true. So we know from over here, we know that P is true because we're told we have that. On the second one now, if P is true, this gives us true, then Q. Now, this is a true statement. So going back to what we did last time, if a conditional statement is true and the if side is true, can we make a conclusion about Q?
It has to be true.
That's correct. Q must be true. So if you have an if-then statement, an if-then statement looks like this. That's the only time an if-then statement is false, is if the if part is true and the then part is false. So here we have the if part is true. So if this statement is true, Q also must be true. Good. If you have an if-then statement that looks like this, you can't make any conclusion about Q. If an if-then statement begins with a false, it's always true. So you can't make any conclusion about Q here. So that was good. So now we know that Q is true. All right, so this goes over here, here. Now from here, so now I'm going to use if-then to talk about if-then. We have now concluded logically that statement Q is true. So if statement Q is true, what's this?
False.
Because Q is true, now we have not that. So now we have false or R. Well, this is an or statement. It must be true. If this side is false, this side must be
True.
True. And so this conclusion is valid. Now, you could go back and replace this with all kinds of stuff. P could be something talking about some kind of a derivative. Q could be talking about something continuity. And then we could have differentiability, and our conclusion would be this. So this is valid. And here again, this is an example why we cannot use the words true or false. We don't know anything about these. These are just symbols. what we just did, basically, or essentially, this should feel like you just did an algebra problem with just X's and Y's that don't mean anything, and you have these rules for manipulating them around. So this argument is valid. Okay. Try another one of these. Oh, questions about any of this yet?
I have a quick question.
Doesn't even have to be quick.
Before when you said that an argument being valid or invalid having no connection to true and false,
Right.
were you just using the words true and false in the sense of like in our reality, true or false, not so much as like if P is true? Do you kind of get what I mean?
Talking about it in any reality. So here, you see why the words true and false don't apply here, because we don't know what these words are at all, right? So we just assume whatever this is, it's true because it's a premise and therefore it's true by definition. What you want in the real world, and this is a good question, Zane, what we want in the real world is an argument that is valid, means logically correct, premises, conclusion, and we want all of those statements to be true. So you want a valid argument and you want all of the statements to also be true, and that's something called a sound argument. So the definition of a sound argument is an argument that's valid and each statement is true. And that's what we're after. That's the goal, and that's how you discover new things. Does that sort of answer what you were thinking about?
Yeah, that definitely helps.
Yep. Okay.
Thanks.
Yeah. Some people don't like doing these, by the way. Some people do like doing these. Some people don't like doing these, but your brain don't care whether, your brain's not gonna care whether you like them or not. It's gonna wanna figure it out because that's just the way, that's just the way humanity goes. So let me see, let me pull up another one of these. I don't like that one. And some of the arguments will be words and some won't. So let me, hang on a minute. Let me pull up a question of my own. Where's the arguments here? Hang on a minute. I'm getting there. Okay, here we go. Yeah. So this one's not in the book. This is just mine. So M or K. All right. So there's the first premise. So because that's true, we know at least one of those has to be true. If M, then Z. If Z, then parentheses, W or not M, then not K. Conclusion, therefore, W. All right, now there's no rules to where you have to start in an argument. You just start somewhere. And premises are commutative, by the way. What do I mean by premises are commutative?
Like you can do them in any order and you'll still get the same outcome.
Right. So there's, yeah, exactly. 1, 2, 3, 4. You can mix these up any way you want. Still going to be the same argument. Okay. So where do we want to go first? I know this is only the second one you've seen. So your brains are thinking now. You're thinking abstractly. You're doing honest to goodness mathematics right now.
Well, I would do, if you could do it in any order, I would say it's not K. So that, and we know number one is M or K. So then therefore it must be M.
Excellent. So from premises, perfect. So from premises 1 and 4, we know that M, whoops, wait a minute. So go ahead, say what you said again. So we know, so here we have from this one, not K is true because that's a premise, right? This is a premise, not K. That's a true statement. So from that, what do we know about K?
K is false.
Right. This is algebra, right? Here you have negative K equals T. So you multiply negative, negative, and then you get not true over here. You see how that looks just like algebra? I multiplied both sides by the word not. I multiplied both sides by the negative sign, and not true means false. Okay. So now we know that K is false. So we have M or something false. So that tells us that M must be
True.
M must be true. So therefore, M is true. All right, let me pause there. So this is why the truth tables for these things, they're awful and they don't really exercise normal thinking. That's why I like to go through these like this. Okay. So from 1 and 4, we now know that. Anybody got a question? That's probably a hard question to answer. I do have a question, but I'm not really sure what that question is. It's probably what you're feeling right now. All right, so here's what we know so far. We know that K is false, and we know that M is true. Okay. What else do we now know?
That C is true.
Okay, so you're looking at premise 2.
Yes.
So how come Z must be true?
Because M is true.
We now know since M is true, so from premise 2, we have true, then Z. Well, I should do my Z's like that. It's an if-then statement. If the if side is true, the other side has to be true for the whole statement to be true. So good, Michaela. So now we know that Z is true. All right, so we use premise 1, we've used premise 4, we've used premise 2. I guess we can conclude that we have to use this. So we now know that Z is true. So Z is true, so therefore this part must also be
True.
Right, because if you have a T on the if side, this side has to be true. That goes back to what we did in the last class. So because from premise 3, we know that W or not M must be a true statement. All right. So where do we go from here? Is this a valid conclusion?
Yes.
Okay, why?
Because M is true, so not M is false, so W would have to be true.
Right, so this is false because we declared M is true, so not M, the negative of true, not M is false. So now we have an or statement, one side is false, so the other side has to be true, and therefore that's valid. So that argument is logically correct.
Are you saying by the end, is that final statement saying that W is true?
Yes, because it's just the letter sitting by itself.
Oh, I see. Again, it's a statement.
Right, so remember, you're correct, W is a letter, but W represents a simple sentence, like the moon is round, right? Or Wisconsin is in New Jersey or something like that. Yeah, each of these letters is actually a whole statement. So some of the arguments you're gonna get for homework are actually all English words, like where was the treasure in the kitchen by the house by the lake, that kind of thing. So the arguments are all the same. By looking at things without words, we begin to pick up on you really can make different conclusions about some things. And it helps us a little bit when we start to think critically outside of a class. Okay, so let me see here. What else I got? Hang on a minute. Pull something else up. I put one up with words, but it's way too much effort to write all those sentences. So I'm just going to do another one with symbols. And the homework, I have stuff all typed out for you. Remember, being a good math person means you're like really, really lazy. All right, so let's try another symbolic. So these are symbolic arguments. There's a couple of those that'll be in the homework, and then there's a bunch that actually have words to them. In her book, there's something about somebody gets murdered and you got to figure out who the crime is and all kinds of delightful things like that. All right, so here's another symbolic argument. So just in general, so you've only seen a couple of these so far. So do these seem like awful or maybe even a little bit fun in some sense? Got an opinion yet? Yeah, that's what I thought. What?
I like them.
Yeah. So, and like some people don't like them, some people do, but you know, so one of the best skills in mathematics is to be lazy. That's kind of a rule, right? What's one of the biggest questions of all in mathematics? For anybody who takes a math class anywhere, what's one of the biggest questions everybody has, whether they say it out loud or not? When am I ever going
to use this?
When am I ever going to use this in real life, right? That's this is all this geometry stuff, all this algebra. When am I ever going to use this in real life? Well, every day is my answer. Whether you know it or not, you're always thinking, should I do this or not that? Well, if I do this first, then I'll have to do this one second, and that'll make me late for here. So I guess conclusion is I'm not going to do that. I mean, we do this stuff all the time. Often we construct a really good invalid argument to justify doing something we know we shouldn't do, right? So we're really good at that. All right, so here's three statements. P and not R, therefore Q. P or Q, and if Q, then P, therefore R. So, valid or invalid? No, this one doesn't seem to have a good starting point, does it? So all three of these are all true, but we're not given a jumping off point. We don't know anything about P, Q, or R except they have these relationships. So what's one thing we can do?
Can we solve it like a systems of equations?
There is a way to do that in logic, but it's not going to work on this one. So here's an example of we don't know where to start. So we start by just making an initial assumption and see where that takes us. So we can start by cases. So case one, let's just assume that Q is true. Now we could be wrong, but we'll find out. If by assuming Q, and we go through all of this and don't come up with this, we'll know that this assumption was wrong because Q is either true or false. So let's just see what happens if Q is true. All right, if Q is true, what does that tell us about P?
It's also true.
Right, so we have if true, then so P must be true. If we assume Q is true, now we know that P is also true. So this says true or true. Okay, that's consistent. My assumption about Q being true doesn't violate whether this is true or not. So now we can go back up to here. If P is true, so now we go up to premise 1, and now we have true and not R, therefore true. All right, so P is true and Q is true. Can we make any assumption about here? Well, here's an and statement, but did we just hit a roadblock?
Yeah, because in order for that to be true, not R has to be true, which means that R has to be false.
Well, so for an and statement to be true, both parts have to be true. That's correct. And that would mean that not R is true, which would mean R is false. And that would make this argument invalid. Excellent. But here's the problem. We have an if-then statement. And all we know is this side is true. This side could be what? This,
False.
It could be
this
false.
side, so if the if part is false, then the whole statement's true. So whether this is true or false or not doesn't contradict anything up here that we've done. So we've gotten into a black hole here where we can't make any decision. So that got us nowhere. All right, so that got us nowhere. So all of our reasoning was logical. So the only problem must have been is that our assumption that Q is true, that assumption must have been incorrect because we couldn't come up with valid or invalid. So the only thing, the thing that kicked all this off was this assumption. So that assumption didn't get us anywhere. So now we'll go back and we'll do case 2. Now we'll assume that Q is false. Okay. Now, if this is false, can we make any conclusion about this? If we have, so from premise 3, if we have false, then P, can we make any conclusion about P?
No.
No. If you have an if statement that looks like this, if an if then starts with false, they're always true. Doesn't matter. So that doesn't help. Oh, but we go to premise 2. If we know this is false, now we know this must be
True.
right, an or statement. This is false, this is true. So now we know that P, under this assumption, P must be true. All right. If P is true, that still doesn't tell me anything about Q. All right. Going up to premise 1, we now have true and not R, therefore Q. Now, we know that Q is false. We know that Q is false, right? So now, on an if-then statement, for this to be true, what must this side of the if-then statement be?
False.
This has to be false. You can't have if T then true. So this must be false in order for this statement to be true. So for this to be false, we have true and something. So the only way an and statement is false, if one of them is true, the other one must be, this is a hard,
False.
right. So now we know that not R has to be false in order to make this false. But if not R is false, that means that R itself is true, which is what we have here. And this therefore is a Valid argument. That was a hard one. That one was a hard one. All right. That's it for today. Anybody got any questions?
I do have one. So I don't think that this is at all like possible, but for this one, we wouldn't have been able to start at the conclusion, right? Like we wouldn't have been able to say, assuming R is true. So almost like assuming it's valid and then try and work our way backwards. That wouldn't be allowed, right?
That's correct. That's called, so this is a logic class and a math class. You can also have a logic class in the philosophy department. And then it's more verbal. They do all the symbol stuff in here, but there's things called denying the premise, there's a whole bunch of words. There's ad hominem faults. That's where you judge the person talking and you judge the validity of an argument that way. It's how advertising works. Oh, this really famous person wears these sneakers. I guess I'll buy those sneakers. So you can't assume the conclusion is true. That's like going into a courtroom and assuming that person's guilty, right? So,
Right.
But you personally doing that may lead you to a way to approach the argument from a more correct way. So you need to show that the conclusion has to fall from the premises themselves.
Okay. All right. That makes sense. Thank you.
Yeah. So this one was a kind of tough one because there was no starting point, but that often happens in a math class. If you think in algebra, so let's assume X is bigger than 2, and then you go from there. Or case 2, what if X is less than 2, and you go from there. So these things come up. So this one was a little bit tough. That's okay. So I'll send out some homework. I have another class right after this, so the homework won't be up for a little while. And then you have a whole bunch of days to think about these things. And we'll get back together on Monday and see how we all did. All right. Okay. So let me stop the recording here.